The paper presents the detection of 661 known pulsars observed with the Australian SKA Pathfinder (ASKAP) telescope at 888 MHz as part of the Rapid ASKAP Continuum Survey (RACS). Detections were made through astrometric coincidence, with an estimated false alarm rate of 0.5%. Using archival data at 400 and 1400 MHz, the authors estimate the power law spectral indices for the pulsars in their sample, finding a mean spectral index of 1.78 plus or minus 0.6. However, they also find that a single power law is inadequate to model all observed spectra, with up to 40% of the sample showing deviations from a simple power law model when incorporating flux densities between 150 MHz and 3 GHz from various imaging surveys. Stokes V measurements from the RACS data were used to measure the circular polarization fraction for 9% of the sample, with a mean polarization fraction of approximately 10%, consistent between detections and upper limits. The dispersion measure, DM, derived distance was used to estimate the pseudoluminosity of the pulsars, but no strong evidence for a correlation with the pulsar's intrinsic properties was found. The paper highlights the complexity involved in modeling a pulsar's magnetosphere and the lack of a complete theory of pulsar emission that explains the diverse observed emission properties. Observational evidence, such as spectral and polarimetric signatures, can provide clues about the underlying emission mechanism. The observed spectrum in pulsars is typically characterized by a steep power law, and pulsars are one of the few object classes in which the emission can be highly polarized, both linearly and circularly. The authors also discuss the traditional method of discovering pulsars through periodicity searching techniques, where the signal is dedispersed and then searched for periodicities. Follow-up observations then add up the emission from individual pulses in phase. Average properties like flux densities can be difficult to measure reliably from such observations. Radio pulsar detection and characterization typically rely on targeted observations, requiring accurate knowledge of telescope gain, sky background temperature, and pulse duty cycle. However, continuum emission from interferometric images offers an alternative approach, as demonstrated by imaging surveys that have successfully discovered and characterized pulsars, such as PSRJ 218 plus 4232 and PSRJ 5237125. These pulsars were initially identified as steep spectrum, highly polarized sources and were found to be brighter than previously discovered pulsars in the Large Magellanic Cloud, but might have been missed in blind periodic searches due to their large pulse width and steep spectrum. Imaging surveys have also identified transients with unusual polarization properties and variability, allowing for the study of their spectral and polarimetric properties and the discovery of pulsars. The spectral properties of pulsars are typically modeled by a power law, with a power law index alpha ranging from 1.4 to 1.8, although some cases require more complex models. Polarimetric measurements have found linear polarization to be around 2040% and circular polarization around 810%, with a high degree of scatter. This study presents the results of a search for detected radio pulsars using the Australian SKA Pathfinder telescope, which achieves a resolution of 15 arcseconds. The study utilizes total intensity and circular polarization sky maps and source catalogs to detect and characterize the radio emission from pulsars. The methodology involves data reduction in pulsar sample selection, followed by a presentation of source properties, including astrometry, flux densities, and polarization properties. The study aims to provide a comprehensive understanding of radio pulsar detection and characterization using interferometric imaging. This research paper delves into the analysis of pulsars using data from the Rapid ASKAP Continuum Survey, RACS. The study initiates with a description of the data collection and reduction process, which entails processing data through the ASKAP soft package for flagging, calibration, and image generation. Flux density calibrations were conducted using PKSB 1934638 as the primary reference source. The sample selection process involved identifying pulsars from the ATNF catalog within the RACS-DR1 footprint, excluding those associated with globular clusters and those with astrometric positional errors larger than 10 arcseconds. This yielded a sample of 2235 pulsars. The spatial distribution of these pulsars is depicted in Figure 1, with most detections situated along the galactic plane. The spatial offsets between RACS detections and ATNF catalog positions are presented in Figure 2, revealing that approximately 98% of Stokes I detections and 100% of Stokes V detections are within 5 arcseconds of the pulsar's position, suggesting that most candidates are likely pulsar cross-matches rather than background noise. The paper also discusses the identification of a source in the vicinity of the pulsar B135362 as part of a search for circularly polarized sources in the Variable and Slow Transients (VAST) survey. Follow-up observations with the ultrawide low receiver on the Parkes 64 meters Murray-Yang radiotelescope confirmed that the polarized source was indeed B135362, with pulsations visible from 700 MHz to 4 GHz. Consequently, the position of the pulsar was updated to RA 13 hours 56 minutes 55.4 seconds and DEC 62 degrees 30 feet 07, with an uncertainty of 2.5 arcseconds in either direction. The paper concludes by discussing the implications of these results, combining them with past studies, and outlining potential future work. The authors analyzed the completeness of the RACS survey by examining the distribution of pulsars detected as a function of their flux density. The observed number of sources per flux density bin is shown in Figure 3, with a power law fit assuming a uniform spatial distribution of standard candles. The best fit power law index is 1, indicating a two-dimensional distribution of sources in the galactic plane. The survey is found to be complete above a flux density level of approximately 2 mJy for Stokes I detection, which is higher than expected based on the noise in the RACS images. A similar analysis for Stokes V sources is challenging due to the small number of sources per bin, but the completeness limit estimated for Stokes I appears consistent with the Stokes V population. A nonparametric test, the Anderson-Darling test, is used to compare the astrometric and spin properties of pulsars detected in RACS with the overall population of pulsars from the ATNF catalog. A deficit in the number of pulsars detected near the galactic plane is found, which can be attributed to the increased background noise in this region. Furthermore, the authors investigate the effect of diffractive scintillation on flux density uncertainties, which can cause additional uncertainties in flux density measurements. They describe the strength of scintillation using the diffractive scintillation bandwidth and timescale, and estimate the fractional error in flux density due to scintillation. This analysis delves into the spatial distribution of known pulsars in the RACS survey, focusing on their cross-matching with the ATNF catalog, and the impact of diffractive scintillation and refractive interstellar scintillation on flux density measurements. Figure 1 illustrates the spatial distribution of RACS sources with ATNF pulsar crossmatches, emphasizing the declination limit of plus 41 degrees for RACS data release 1. It reveals 661 pulsars with RACS counterparts within 10 inches, among which 168 have measured flux densities at 400 MHz and 1400 MHz. Figure 2 showcases the distribution of spatial offsets between ATNF catalog positions and RACS positions for pulsar crossmatches, demonstrating the precision of the RACS survey. The study explores the effects of diffractive scintillation on flux density measurements, finding that most pulsars in the sample exhibit fractional errors below 0.5, but a few, approximately 2.5%, have errors exceeding 0.5. Corresponding to a dispersion measure, DM, limit of roughly 10% per cc. It also delves into refractive interstellar scintillation, RIS, estimating the fractional error in flux density due to RIS for the pulsars in the sample, which ranges from 6% to 18%, 16th and 84th percentiles. The spectral index distribution is also examined, with the authors conducting a least squares fit to determine the spectral index, assuming a power law distribution, utilizing flux densities at 400 MHz, 888 MHz, and 1400 MHz. They exclude 18 pulsars that display non-monotonic behavior and cannot be modeled by a single power law. Table 2 provides the flux density measurements for the 168 pulsar sample, which will be employed in further analysis of the spectral index distribution. Figure 3 presents the number density distributions of Stokes I and Stokes V sources as a function of flux density at 888 MHz. The observed distribution is shown in red, while a power law fit assuming a two-dimensional galactic distribution of standard candles with beta equals -1 is represented by the dashed black line. The survey is found to be complete above approximately 2 MJY. The distribution of galactic latitudes of detected pulsars is displayed in Figure 4, comparing the RACS survey results, blue histogram, with the overall distribution from the ATNF catalog, green histogram. A deficit in detected pulsars is observed for B less than 8 degrees, which is mitigated by removing detected pulsars below 3 MJY, resulting in a distribution that traces the expected population. The authors highlight the limitations of power law modeling for pulsar spectra, citing complex spectral behavior and variability among non-simultaneous measurements. Figure 6 showcases 18 pulsars that exhibit non-monotonic spectral evolution, which cannot be described by a power law. Among the remaining 150 pulsars with monotonic spectral variation, only 60% can be adequately modeled by a power law, with a goodness of fit. Reduced chi2 is less than or equal to 2. Figure 5 illustrates the fractional error in flux density due to diffractive scintillation as a function of dispersion measure for pulsars identified in RACS data. Only a small fraction of pulsars, 2.5%, are strongly affected by scintillation, primarily those with dm less than 10% per cc. Most pulsars with a fractional error greater than 0.1 have dm less than 40% per cc. Finally, Figure 7 highlights the inability of a single power law to accurately model the observed spectral variation, showing the ratio of observed to power law modeled flux densities for the sample of 150 pulsars. This research paper explores the spectral energy distributions of pulsars, focusing on deviations from monotonic trends and the limitations of using simple power laws to model these spectra. A sample of 150 pulsars is presented, with approximately 40% exhibiting non-monotonic spectral energy distributions. These deviations are evident in Figures 6 and 7, where observed flux densities significantly deviate from power law models at 400, 888, and 1400 MHz. The study highlights that these deviations cannot be attributed solely to RIS, radio interference and scattering, due to the high prevalence of pulsars with non-monotonic spectra. Instead, it suggests that intrinsic variability and temporal variations could contribute to these deviations, although the exact causes remain unclear. The distribution of spectral indices in the sample of 150 pulsars is presented in Figure 9, showing that using different sets of frequencies for the fit results in varying distributions. This indicates that the source spectrum may deviate from a power law in the presence of low-high frequency deviations. The findings of this study underscore the importance of considering more complex models to accurately describe the spectral energy distributions of pulsars, as simple power laws are inadequate for a significant portion of the sample. This research contributes to our understanding of pulsar spectra and emphasizes the need for further investigation into the underlying mechanisms causing these deviations. The spectral index distribution of pulsars in the RACS survey is presented, utilizing flux densities measured at 400 and 1400 MHz. The mean spectral index is 1.78 plus or minus 0.6, consistent with existing literature. A correlation analysis between spectral index and pulsar period reveals no strong evidence for steeper spectra in recycled pulsars compared to normal pulsars, aligning with previous studies. Polarization fraction measurements range from 0.5% to approximately 70%, with most detections exhibiting values consistent with literature values, and a median of approximately 10%. However, fractions below 1% may not be reliable due to leakage of flux into Stokes V in the RACS data. The Kaplan-Meier estimator is employed to account for non-detections, resulting in a mean polarization fraction of 4.6% with a large spread of plus or minus 8.4%. The calculation of expected luminosity for a pulsar in a given frequency band is challenged by the unknown underlying source spectrum. This limitation underscores the importance of understanding the intrinsic emission spectrum of pulsars. Key findings include a mean spectral index of 1.78 plus or minus 0.6, no strong evidence for steeper spectra in recycled pulsars, and polarization fractions ranging from 0.5% to approximately 70%. Methodologies employed include spectral index calculation, correlation analysis, polarization fraction measurement, and the Kaplan-Meier estimator. Figures 9, 10, and 11 illustrate the distribution of spectral indices, correlation between spectral index and pulsar period, and distribution of polarization fractions and upper limits, respectively. Limitations include unreliable polarization fractions below 1% and unknown underlying source spectra. Future work may involve investigating the intrinsic emission spectrum of pulsars and further analyzing the polarization fraction distribution. An analysis of the polarization properties and luminosity of known pulsars in the RACS-9 sample reveals complex behavior. The circular polarization fractions for pulsars detected in both Stokes I and Stokes V are presented in Figure 11, along with upper limits for non-detections. The distribution of polarization fractions peaks around 10%, with few pulsars exhibiting higher polarization fractions. The mean polarization fraction is estimated to be 4.6% using the Kaplan-Meier estimate, with a 1 sigma spread of 8.6%. The pseudo-luminosity of pulsars, defined as S nu d2, where S nu is the flux density at a frequency nu and d is the distance to the pulsar, is computed for all pulsars in the sample using measured flux densities at 888 MHz. The radioluminosity function for pulsars is typically expressed as L nu equals AP gamma 1 P gamma 2, where the indices, gamma 1, gamma 2, are estimated from observations. Correlations between the pseudoluminosity and pulsar parameters such as period derivative, characteristic age, and magnetic field are explored. Figure 12 presents correlation plots of pseudoluminosity versus pulsar parameters, using electron density maps from Yao et al. 2017, and Cortis and Lazio, 2002. No clear evidence for strong correlations is found. The radioluminosity is computed and compared to spin-down luminosity, revealing that the radioluminosity does not scale accordingly with the spin-down luminosity. The luminosity ratio, radio to spin-down, decreases with increasing spin-down luminosity, suggesting that varying fractions of spin-down luminosity power the radio emission in pulsars as they age. The Spearman rank correlation test is employed to quantify the level of correlation. Table 1 presents the Spearman correlation coefficients for pseudoluminosity versus intrinsic pulsar parameters and existing correlations in the literature. The sample is dominated by normal pulsars, and the correlation test is restricted to these objects. The results indicate a lack of strong correlations between pseudoluminosity and pulsar parameters. The findings have implications for our understanding of pulsar emission mechanisms and the relationship between radioluminosity and spin-down luminosity. The correlation between pulsars' pseudoluminosity and their spin parameters, characteristic age, magnetic field strength, and combinations of these parameters is examined. Figure 12 presents correlation plots that reveal no strong intrinsic correlation between pseudoluminosity and any of these pulsar parameters. However, a distinction is evident in the spin parameter space between normal and recycled pulsars. The correlation coefficients in Table 1 further confirm the lack of strong correlations. The study also compares spectral fits from the RACS and PSRCAT surveys with measurements from other all-sky radio imaging surveys, including TGSS, MWA, and VLAS. Figure 13 displays this comparison, where residuals are the ratio between observed and modeled flux densities are calculated using a power law fit. If the source spectrum can be well modeled by a single power law, the residuals should be consistent with zero within error limits. Any additional variation may indicate more complex spectral behavior, potentially deviating from a single power law. This analysis provides insight into the pulsar's spectral properties, highlighting potential deviations from simple power law models. The authors of the research paper compare the predicted flux densities at 150, 200, and 3000 MHz using the spectrum estimated with RACS and PSRCAT data, to the measured flux densities from other imaging surveys. The residuals, as shown in Figure 13, demonstrate that a single power law estimated from the ATNF and RACS data greatly overestimates the flux at these frequencies in many pulsars, suggesting evidence for low and high frequency deviations from a power law model. To better model the data, the authors fit a quadratic power law, lane, S nu, equals ALN, nu, squared plus BLN, nu, plus C, to the flux density measurements of a sample of 35 pulsars. The bottom panel of Figure 14 shows the residuals in this case, demonstrating that the variation is better modeled by a quadratic power law, with uncertainty normalized median residuals of approximately 0.3 sigma, 2 sigma, 0.6 sigma, 0.8 sigma, and a median reduced chi-squared of 1.7, 3 DOF. The authors also find that a broken power law performs comparably to the quadratic power law. Figure 15 illustrates the spectra of 14 pulsars that have flux density measurements in multiple surveys, demonstrating that deviation from a simple power law is common, and a quadratic power law or broken power law provides a better fit to the data. However, the authors caution that even a quadratic or broken power law may be inadequate to model the spectrum in some cases, such as when the spectrum exhibits both low-frequency turnover and high-frequency turnup. They conclude that the spectrum in a modest set of pulsars, as large as 40%, does not seem to exhibit a linear variation in logarithmic frequency flux density space, and hence the use of a simple power law spectral fits in pulsars must be treated with caution. The authors present a spectral characterization of 14 pulsars, utilizing flux density measurements available at multiple frequencies including 150, 200, 400, 888, 1400, and 3000 MHz. The spectra are modeled using a simple power law, a quadratic power law, and a broken power law. Results indicate that a single power law is often inadequate, with quadratic or broken power laws providing better fits to the spectral shape in many cases. This nonlinearity in the variation of flux density with frequency in logarithmic space is evident in Figure 15, which displays the spectra of the 14 pulsars. For example, the spectrum of J04521759 prefers a quadratic or broken power law over a simple power law. Cross-matching known pulsars with the first release of the ASKA PRACS survey data results in 600 Stokes I sources and 61 sources with both Stokes I and Stokes V matches. The estimated false match rate is 0.5% with 95% confidence. Polarization information of these sources is also examined, revealing an estimated fraction consistent with previous literature. An investigation into the variation of pseudoluminosity and its correlation with intrinsic pulsar parameters reveals no significant evidence for a strong correlation. The addition of reliable flux density measurements through current and future surveys, such as TGSS, MWA, and VLAS, can be used in more advanced spectral modeling. The data presented can be added to repositories like Swainston et al. 2022, for further analysis. The authors acknowledge the support received from various organizations, including the National Science Foundation, the Australian Research Council Centre of Excellence for Gravitational Wave Discovery, and the Australian Government, in facilitating the research presented in this paper. Utilization of facilities such as the CSIRO Murchison Radioastronomy Observatory, the Australia Telescope National Facility, and the Pawsey Supercomputing Research Centre is also acknowledged. The authors recognize the traditional owners and native title holders of the observatory site, the Wajari Yamaji people, demonstrating respect for the land and its indigenous heritage. The research employed software packages including NumPy, Matplotlib, and AstroPy for data analysis and visualization, underscoring the importance of robust computational tools in radio astronomy. Notably, the authors emphasize the significance of known pulsars in radio astronomy surveys, such as the RACS survey, for accurately modeling the underlying source spectrum of the pulsars. This highlights the critical role of pulsars as celestial beacons in understanding the properties of radio sources. The appendix section commences with a focus on image cutouts, providing supplementary visual information to support the findings and discussions presented in the paper. This section is likely to include images of pulsars or radio astronomy data, offering a visual representation of the research outcomes. The inclusion of such visual aids is crucial for facilitating a comprehensive understanding of the research, allowing stakeholders to engage with the data in a more intuitive manner. Figure 16 presents 3 case studies of Stokes I and Stokes V intensity maps, showcasing the detection of pulsars PSRJ 0711680, PSRJ 528 plus 2200, and PSRJ 509 plus 0856. These images are 3 feet cutouts, with the detected RACS source marked by a red ellipse and the pulsar's position from the ATNF catalog indicated by crosshairs. In panel A, the Stokes I map of PSRJ 0711680 exhibits a clear detection, with the pulsar's position coinciding with the peak intensity. The right ascension, RA, and declination, DEC, values are provided, along with the corresponding Stokes I intensity values. Panel B displays the Stokes I map of PSRJ 528 plus 2200, where a detection is observed, although with a marginal Stokes V detection. The RA and DEC values are listed, accompanied by the Stokes I intensity values. In panel C, the Stokes I map of PSRJ 509 plus 0856 shows a pure Stokes I detection, with no corresponding Stokes V detection. The RA and DEC values are provided, along with the Stokes I intensity values. The lower row of Figure 16 presents the Stokes V maps for each pulsar. Panel D displays the Stokes V map of PSRJ 0711680, where a clear detection is observed. Panel E shows the Stokes V map of PSRJ 528 plus 2200, where a marginal detection is seen. Panel F presents the Stokes V map of PSRJ 509 plus 0856, where no detection is observed. These case studies demonstrate the efficacy of the RACS survey in detecting pulsars and characterizing their polarized emission properties. The Stokes I and Stokes V maps provide valuable insights into the pulsar's emission mechanisms and can be used to further investigate their properties. Astrometric and spectral measurements for a selection of pulsars in the RACS sample are presented, focusing on those with power law spectra. The table provides pulsar coordinates, including right ascension and declination, alongside flux densities at frequencies of 888 MHz, 400 MHz, 1.4 GHz, 150 MHz, 200 MHz, and 3 GHz. The spectral index, a critical parameter in understanding pulsar emission properties, is also included. Organized into columns, the data represent various measurements, with each row corresponding to a specific pulsar. Pulsar names and coordinates are listed in the first 2 columns, followed by flux density measurements at different frequencies. These measurements are essential for understanding pulsar emission properties across the electromagnetic spectrum. The final column contains the spectral index, which describes how pulsar emission varies with frequency. A negative index indicates decreasing emission with increasing frequency, while a positive index suggests increasing emission with higher frequencies. This comprehensive dataset of astrometric and spectral measurements is crucial for pulsar researchers, providing insights into the physical processes underlying pulsar emission and furthering our understanding of these enigmatic objects. This table presents a comprehensive survey on pulsars, providing essential information about their properties and behaviors. The pulsars are identified by their right ascension, RA, and declination, DEC, coordinates, with flux densities measured at different frequencies. The data includes information from various imaging surveys such as RACS, ATNF, and others, showcasing the variability in pulsar emission across various frequencies. The first column lists the pulsar names, followed by their RA and DEC coordinates in hours, minutes, and seconds for right ascension, and degrees, minutes, and seconds for declination. The next columns provide the flux densities at 888 MHz, 400 MHz, 1.4 GHz, 150 MHz, 200 MHz, and 3 GHz, respectively. These measurements are crucial for understanding the spectral indices of these pulsars, which can be calculated using the formula S nu proportional nu caret alpha, where S nu is the flux density at frequency nu and alpha is the spectral index. The table also includes spectral indices derived from the flux densities, indicating how the pulsar's emission changes with frequency. A negative spectral index suggests that the pulsar's emission decreases as the frequency increases, while a positive index indicates an increase in emission with higher frequencies. The table highlights the variability in pulsar emission, demonstrating that some pulsars exhibit strong emission at certain frequencies but weak emission at others. This variability could be due to various factors such as interstellar scattering, scintillation, or intrinsic variability within the pulsar itself. In conclusion, this table provides a detailed overview of pulsar properties and their emission characteristics across different frequencies. It serves as a valuable resource for researchers studying pulsars and their behavior, helping to advance our understanding of these enigmatic celestial objects. This table, Table 2, continued, from the research paper presents a comprehensive list of known pulsars in the RACS-17 region. It provides essential information about each pulsar, including their coordinates, right ascension and declination, flux densities at various frequencies, 888 MHz, 400 MHz, 1.4 GHz, 150 MHz, 200 MHz, and 3 GHz, and spectral indices. The table lists 7 pulsars: J2046 plus 1540, J2046041, J2055 plus 3630, J21243358, J21295721, J2317 plus 2149. For each pulsar, the table provides the flux density at different frequencies, along with the errors in flux densities due to diffractive scintillation and measurement uncertainties. These flux densities are quoted in Milihonsky's MJY, and the errors are given in parentheses, representing the 1 sigma uncertainties on the last digits of the flux densities. The spectral indices, which describe the power law behavior of the pulsar's spectrum, are also provided. This table is crucial for understanding the characteristics of pulsars in the RACS-17 region and their potential implications for astrophysical studies. Unfortunately, it seems like you haven't provided the content to refine. Please provide the transcript of the research paper, and I'll be happy to refine it according to the guidelines you specified. I'll transform the text into a concise, technically accurate summary suitable for voiceover narration, maintaining the tone and precision required for expert researchers and stakeholders.